So today I'll be teaching you how to find maximum stresses using Moore's circle. And to do this, we're going to be using problem 7.3-13 from our textbook. And that stress element of the problem is drawn here. Now the first step to doing this is you're going to separate your stresses into two pairs, where pair one is going to be these right here. You have your sigma x. If it's tension, it's going to be positive. If it's compression, it's negative. So in this case, this is in tension. So this is a positive. And then for our shear, we're not going to worry about positive or negative. We're just going to worry about which way it would rotate the stress element. So for example, in this case, our shear stress is going this way. So that would rotate this stress element counterclockwise, as denoted here. And then for pair two, we're going to be doing these two stresses, where sigma y is also in tension, so that's going to be positive. But in this case, our shear stress would rotate it clockwise. So we've denoted that with this arrow. Now it's time to draw our Moore's circle, and you have our x and our y-axis, where negative is compression, positive is tension, and it's all normal stress, but our y-axis is going to be our shear stresses. So then we can plot our two pairs. Those are drawn here with P1 and P2, and we can just connect those and solve for our mean stress, which is going to be that point right there in the middle. Now once we have all that, we can work to solve for the radius of our circle, and that can be solved very easily since we already know that this y value and this x value, and we can just use Pythagorean's theorem in order to find the radius. Now, once we have all that done, we can go ahead and draw our circle and move on to find what is asked for in part A. Now, part A asks for us to find the principal stresses and show them on a sketch of a properly oriented element. So the principal stresses are simply the stresses where the shear is equal to 0. So those are going to be your x-intercepts. Now on our graph, this is going to be pretty easy to find because this is just the radius out from our mean stress. So now that we have our radius, we can just add that to our mean stress to find this intersection, or subtract it from our mean to find this intersection. So now we have our two principal stresses. And now the one thing we need to find now is our angle here when we actually draw our stress element, so we know how to orient it. Well, you can actually easily find that angle here because it's just going to be this theta value that moves the radius from your pair one up to your principal stress. But the key to remember here is on this graph, the angles are going to be twice what they are in real life. So whatever you calculate this theta to be, you just need to make sure to divide it by 2. So once we divide it by 2, we get 7.9 degrees, and that is going to be the angle we rotate our stress element by. Now for part B, they ask you to determine the maximum shear stress and associated normal stress, and then show them on a properly oriented element. Now the max shear is just going to be the very top or very bottom of our circle. And in order to find those, you're simply going to add our radius to where we are here at the max, what our shear is at the mean, which is just going to be 0. So our max shear is just going to be our radius. And now in order to find our sigma max, or in order to find our normal stress at this shear max, it's simply going to be our mean stress because we're just moving straight up from that. We're not moving along the normal stress axis. Now once we have all those, once again, we just need to find the angle. And the angle is just going to be 90 minus the angle that we found before, because as you can see here, this is just a right angle. So once we take the original angle from it, we just need to remember again to divide it by 2, because up here is twice what it would be here, and we get negative 37 degrees. And then we can just draw in our two stresses and rotate it by the angle we found, and there we have our properly oriented stress element.